Everyone. This video lecture is about modeling with exponential functions. And so what we're really talking about is modeling systems that change by repeated multiplication. Before we get into some like application systems, I want to show you how to build kind of an abstract exponential function when given 2 points. So quick review, we can find an equation for a line with 2 points. All right, if I have the points 1, 2, and 3, 19, I can find the equation for a line that goes through these points because I need y equals mx plus b, so I need the slope, which is the change in outputs over the change in inputs, which is 17 over 2 or 8.5. And then I take that information and I update what I know. And then I use one additional point to help me get the missing letter. So I'm going to use the fact that y is 2 when x is 1 and subtract 8.5 from both sides. And we get negative 6.5 equals b. And now I've built an equation, y equals 8.5x minus 6.5, that goes through the points 1, 2, and 3, 9. And the key was we started by finding the linear rate of change. We're going to apply this exact same idea to exponential functions. To find formulas for exponential functions that go through 2 points. So let's find the formula or find an equation for an exponential function that goes through the points 1, 2, and 3, let me think, 128. I think that's going to work. Now, when I did this with the linear function, I was able to do it just pretty much symbolically. But I think for this, it's a good idea to use a table. So first, we're going to remind ourselves of the general form of an exponential function, which is y equals a times b to the x. Now, build yourself a table. It's going to not have a lot of information in this table, but it's going to have 1 and 2, and it's going to have 3 and 128. And the reason to build this table is so that you can count the change in x and the change in y. The change in x from 1 to 3, it went up 2. The change in y, it's a multiplication. And what are we multiplying by? We're multiplying by our exponential rate of change. The change in y was b squared. That 2 and that 2 are exactly related. If your change in x added 2, then your change in y multiplied by b twice, so it multiplied by b squared. And here's where we get really clever. We know that it changed by multiplying by b squared, but we also know that it changed by multiplying by 64 because 64 is 128 over 2. That's the multiplication change. Remember, exponentials change by multiplication. So to get from 2 to 28, we're not subtracting, we're multiplying. We multiplied by 64. So the change in y was b squared. The change in y was also, let's see, times b squared was also times 64. Well, that means b squared must equal 64. That means that b must be the square root of 64, which is, ooh, math, which was 8. This will take a little bit to settle in because it's a different type of change, but the process is similar. How far did I go from 2 to 28? In multiplication, I multiplied by 64. How many multiples was that? B squared. It was 2 multiplications because x went up by 2. So b squared must equal 64, so b must equal 8. And let's just double check. I'm going to rewrite everything. So we have it here on the fresh page. 1, 3. There's our 2. X up 2. B squared went up by a multiple of 64. That implies that b equals 8. And let's check. 2 times 8, 16. 16 times 8, 128. Yep, it worked. So now I have my exponential rate of change. I can fill in some of that information. Y equals a times b to the x becomes y equals a times 8 to the x. And I use a point. We know that y is 2 when x is 1. So 2 equals 8a. Divide both sides by 8. And I get that a equals 1/4. So I'm able to rewrite my whole equation as 1/4 times 8 to the x. And let's go ahead and check. 1/4 times 8 to the first is 8 over 4, which is 2. Yep. And 1/4 times 8 cubed is, I think it's, uh, times 8, 64. That's 512 over 4, which is 128. I'm going to do another one because it just takes practice. I'm happy to show you a couple of these examples for practice. These do come in handy when we're solving in real situations because you might imagine that you were supposed to measure your population of, I don't know, rabbits on day 1, but you got sick, so you didn't measure it on day 2, and you came back on day 3 and there were 128 rabbits. And you're like, wow, that's growing fast. How fast is it growing? And so you can use this process to figure out the function that tells you how fast it's growing, which is this function right here. Yeah, let's do another example. Let's build an exponential equation that goes through the points -2, comma, 80 and 3, comma, 5/2. So if I know I want an exponential equation, the first thing I'm going to do is remind myself what it looks like. A times b to the x, where b is the exponential rate of change. So that's what I'm going to find out first. And I'll build my table. I have a -2 and an 80, and then I'm going to count up to 3, -1, 0, 1, 2, 3, and 5/2. And so I counted 1, 2, 3, 4, 5. So x was up 5. That means I must be multiplying 1, 2, 3, 4, 5. I must be multiplying by b 5 times, but also I'm multiplying to get from 80 to 5/2. So my multiplication factor must be 5/2 divided by 80, because I have to multiply to get there. So I'll double check. 80 over 5/2 is 32. It's always a good idea to double check. Sorry, this should be 1 over 32. My apologies. And I check 80 times 1 over 32. Yes, that's 5/2. So that means b to the 5th must be 1 over 32, because I'm multiplying by b 5 times. So if b to the 5th is 1 over 32, that means that b is equal to the 5th root of 1 over 32, which a calculator will tell you is 0.5 or 1/2. So now I can fill that information in. Maybe I still don't know a, but I do know that b equals 1/2. And now I can use either of my 2 points. Sometimes it's easier to use positive exponents. So let's say that 5/2 should equal a times 1/2 cubed. 5/2 is a times 1/8. So multiply both sides by 8, and I get 40 over 2, or 20, equals a. So my formula is then y equals 20 times 1/2 to the x. And that's how I build my exponential equation. All right, so that's a useful tool. Now let's look at a couple different ways to model systems. So we can look at continuous change. This is always going to involve the natural exponential base, e. So a population of bacteria grows continuously at 7% per hour. If we start with 20,000, I'm going to use 20 because I don't want to carry about big numbers, but if you ever find just 20 bacteria, that's kind of crazy. If we start with 20 bacteria, how many will there be after, let's say, 5 hours? So we say, okay, this is a continuous growth. The 7% tells you that it's multiplication. So it's a continuous multiplication growth. And that means we want to use a natural exponential base b, which is y equals a times e. And we use that percentage, and this is actually very similar to the economic interest idea. A is like our principal, we have our interest rate as a decimal, and X is our number of time periods, in this case, hours. So the general form is y equals A times e to the Rx. A was my initial, so A is 20. The interest rate or the growth rate is 0.07, and there are 5 hours. And so we go over to our calculator, like Desmos, to find what that number is. 20 times e to the 0.07 times 5, and they get 28.38. And again, if I'm thinking in thousands, 28.38 thousand. That's a question I could ask. I could also say, when will the population reach 40? So I still have my equation, y equals A times e to the Rx. A was 20, R was 0.07, and now I want to reach 40 individuals, so I say 40 equals 20 times e to the 0.07x, and now I have an exponential equation where I'm going to solve for x. Again, this is kind of similar to the continuously compounded interest. Divide both sides by 20. 2 equals e to the 0.07x. I can take the natural log of both sides. The natural log and the exponential cancel. And I get the natural log of 2 equals 0.07x. So x equals the natural log of 2 over 0.07, but I'm asking how many hours that is. And even though that's a number, natural log of 2 divided by 0.07, that's a number, but I don't have any idea how big that number is. So I want to get a decimal approximation, and I get 9.9 hours approximately. So if you wanted to come back and harvest your bacteria once you reach 40,000, then you would have to wait for 10 hours about. That's continuous change. Then we have periodic change. This is like compounding once per year. So for example, let's see. A field of carrots is harvested every day, and 20% of the remaining carrots are harvested. If there were 500 carrots to start, how many remain after, let's say, 3 days? So we say, okay, it is a change by multiplication because it's a 20%, but it's not saying the carrots are harvested continuously. They're harvested every day, right? That's the period, every day. And every day they harvest 20%. So carrots, as a function of time, should start with 500 And then we're going to multiply by something raised to the power x, where the x is in days. And what we multiply by is 1 minus 0.2 because they're taking out 20% every day. Because the number of carrots is always what's remaining. So in this case, if we're removing 20%, then 80% is remaining. And now we want to know 3 days. So that's 500 times 0.8 to the third power. And Desmos will tell us that one. 256 carats remaining after 3 days. And you could imagine saying, well, how long will it take until there are 4 carats left, right? And then you would solve for x. That's periodic change. The next one is half-life and doubling time. And all this means is that the half-life, the base, always equals a half, and the doubling time, the base always equals 2. So let's look at a half-life question first. A drug is removed continuously from the bloodstream every 3 hours. Half of the drug is removed. All right, the key here is this half. That tells you that the base is going to be a half. So our formula for this is drug at time x. Oh, yeah, the initial dose was, let's say, 400 milligrams. So again, we start with our initial 400, and now the base is just always going to be 1/2. And what changes here is the exponent, because it's every 3 hours, half of the drug is removed. If I put x here, that would say every 1 hour, half of the drug is removed. So I need to slow down that process. And to slow it down, I take x and I divide it by 3. So the general formula for half-life is initial value times a half to x over the half-life. And doubling time is very similar. This is half-life. With doubling time, you take your initial times 2 to the x over doubling time. Usually the change is continuous, but they don't give us a continuous rate. They just tell you after how many time periods half is left. So the formula for half-life is the initial value times 1/2 raised to the x over the half-life. And the doubling time is the initial value times 2 raised to the x over the doubling time. All right, let's take this question, the drug being removed and every 3 hours half is gone, and let's find out the continuous rate of change. So we're going to start with d of x equals 400 times 1/2 to the x over 3, and we want a continuous exponential rate of change, so we need to find the same model with a times e to the rx, right? We want to change it and we want to find the r that would build us the exact same model. There are a lot of ways to do this, but I'm going to use that method I showed you at the beginning of this video and put this in a table. So I wanted d of x, which is 400 1/2 to the x over 3, to rewrite it as a times e to the rx. Well, I know what the a is. The a is still going to be 400. And so e to the rx takes the place of the 1/2 x over cubed, x over 3. So I'm going to build a table with this information. Here's my x, here's my d of x. And I happen to know when x is 0, there are 400 milligrams. And I also know, because of the half-life, that after 3 hours, half of it remains. So I get 200. So x went up 3, and I must have multiplied the 400 by the e to the rx. So I must be multiplying by e to the r times 3, or e to the 3r. If I went from x equals 0 to 3, took me from 400 down to 200 by multiplication, then I must have had 400 times this term equals 200. 400 times e to the 3r must equal 200. So e to the 3r must be that multiplication, which was a multiplication by a half. And now I have a nice exponential equation. E to the 3r must equal that 1/2 multiplication, and I solve for r. Take the natural log of both sides, cancels over here, and I have 3r equals natural log of 1/2. Divide both sides by 3. And let me get a decimal approximation for natural log of 1/2 over 3. It's negative 0.231. R equals negative 0.231. R is negative because my change itself is going down. So that makes sense. So my model must be d of x is 400 times e to the negative 0.231 r. And I can check that. D of 0, definitely going to be 400. D of 1, let me do D of 3, because that's got to be 200. So it should be 400 times e to the negative 0.231 times 3. And if you check it in the calculator, yes, in fact, that is equal to 200. So let me recap this, and it's going to build us a little bit of a shortcut, which honestly I didn't see until I did it this way. So if the half-life is n periods, then you can find the continuous percent by e to the n times r equals 1/2. We said n time periods, so we had e to the 3r equals 1/2 if n equals 3. And if n equals 10, then it would be e to the 10r equals 1/2. So that's going to be a nice, much simpler way rather than building the table each time, which you could do. But now we have a nice formula that converts from half-life with a 1/2 to the x over n to a continuous change. And it's going to work the same way for doubling time. If the doubling time equals n, then e to the nr equals 2 produces the interest rate, the continuous growth rate r. All right, that wraps it up. Thanks for watching.